Okay, hi everybody. I was sleeping and then I had an idea that solved all of my problems. And then I'm really frustrated because now that means I have to get out of bed in order to write it down so I don't forget them. This video is about a very special shape that is a single shape, but it tiles. But oh no, it doesn't just tile. It tiles in a way that will never show the same pattern twice. Which is good for me because I like variety and I hate repeats. So, also, it's good for everybody in existence because it creates the first, or the groundwork for the first non-absolute, no, that's the wrong word. The first centerless absolute coordinate system. Let me show you what I am talking about now. Yeah, that's good. We'll start there. Then we'll go to my favorite little app I always use. And we'll go here, there, everywhere, and here. And then we'll go to crop, square, lock ratio, get a nice full frame for what we're about to do. A nice full frame. But try to get as much variety inside of it as possible without showing empty spaces. Yep, that looks like exactly what we want. Okay, almost there. Alright, everybody. Now, there's this little thing called the four-color theorem. It holds for any two-dimensional plane, which means that this complex mess can be sorted and organized and then reverse engineered. First, I need to make my life easier, which means it's time to thicken some lines. Make that black. Make it fully opaque. Make this a little less fuzzy and a lot a bit smaller. Or actually, large is good because we're going to need to zoom in anyways. Zoom in, sorry. And maybe not that large. And maybe not that. Well, you know what? Doesn't matter. Let's go. Okay, this is just a rough approximation. We would create a computer program to make this more exact, obviously, in the final version. And here we see that one of the lines didn't quite render well. Ah, I see. Here it is. That's just a lighting issue. Okay. Hope you guys are still following me. Yep. And then... swoop. Oops. It'll be worth it, trust me, guys. Why don't I just do all the work and then show you when I'm done? Okay, I've converted it into just line art. And now I'm going to make a four-color theorem approximated result purely for conceptual demonstration. It won't be algorithmically rigorous. Okay, you can see here that I have given it four colors, although I think in this case it only needed three. I may as well use some artistic liberty since it isn't mathematically verified to be the correct algorithm anyways, since this is just a demonstration of concept. Now, we go here, and we add one of these. Looks about right. We don't actually want... Oh, wait, hold on. Hold on. We want a nice middle gray. 0 saturation and 50% value. Okay. Alright. That looks about right. And then instead of dragging the corners, we'll manually change the size. I'll just take a guess here. Let's see. You don't want to double the radius. Looks like all the way to the edge is slightly less than 1/4. So let's increase it by 1/8. Alright. Clear. 1, 1, 1 divided by 8 equals plus 1, 1, 1. Round that up. Alright, go back here. 125. 125. Hopefully the origin is in the center. Looks about right. But it didn't expand as much as I wanted, so let's just skip to 150. Actually, 160 feels like it might be the magic number. Yeah, that looks about like the one I wanted to demonstrate. It's better if it's smaller. Okay. Looks centered. Then we go to frame. And we do a color frame. That is the correct color. Alright. Then we go to the effects. Then we go to sketch. That's the only information I'm worried about. And then we are done. Each one of these black lines, we save that as a vector. This, okay, so let me rephrase. You see this strip? That's the only data we need to save. Just a small band, more or less. Or, how do I put it? A thick outline of a square, and within that thick outline of a square, we have something similar to a vector line format, but specified for this file format. Oh wait, go back. Actually, this is what we wanted to save. We save each one of these black lines as a similar to vector SVG format vector, but not quite, because it's actually just an intersection format. Within the data, we start at some random point, and we unwrap this into a line, so it just looks like this, but really, really long, 4 times as long. Then in the computer, we bend that line back into a square outline, and then using the color for the partial area data and the vector for the partial outline data, we use, that should be a high enough resolution for most, if not all, reconstructions of local areas of the infinite void. Essentially, instead of a coordinate in a coordinate space, we use a texture inside of a narrow frame, a vector texture with 2 bits of color, and with 2 bits of color and vector data, we can use a thing similar to an autocomplete algorithm or a Sudoku solver algorithm to fill in the gaps inside and outside of the graph. So with just a narrow rectangular strip of the graph, we can reconstruct the entire page of the graph, and therefore, with a very small amount of information, we can encode our position in space. Within an infinite graph, the only limitation is that the infinite graph needs to be manually translated as part of a continuum gradient. In other words, you slide it until it is partially how do I put it? In other words, you just slide to the side, and then you use the same solver algorithm to fill in the parts that you didn't create yet, and you use a viewport cropping algorithm to forget about the parts that are no longer in the window, and you do that to manually navigate to new places in the space. You start with a random one of these in a, you start with a random one of these. I'm not sure if the angle matters, because the location of the colors might be all that matters. And then you use a valid tiling spiral initially to fill out the frame with one of these located roughly in the center. And from that single seed, you can nucleate an infinite graph. And as long as every partial graph is a capture of some translated area of the nucleated graph from that same seed, then all data related to partial graphs will be in the same graph. Therefore, instead of needing infinitely many coordinates to express a location that is an infinite distance away from a starting point, let me rephrase. Because there is no infinite distance at an actual location. Instead of needing an indefinite number of digits to express a coordinate that is an indefinitely large or arbitrarily large distance away, the same frame size should suffice for any distance from the point at which the graph was originally spawned, as long as you take references from that graph to get those frames. In other words, you have to manually walk there, but after you do that, you can teleport to any other place that is stored in memory, so long as that place was manually walked to that location as well. At least until we develop a spigot algorithm for the seeds for this type of graph structure. In other words, just like the universe does not have a definite structure, this form of graph encoding also does not have a definite structure. Yet, two objects on the same graph can still be stored relative to one another at the same time on the same graph, as long as you're aware of both and the parts that line up with the particular graph. as long as you never rotate the frame and keep everything in the same rotation, and you don't change the colors of the cells using the four-color theorem and the aforementioned algorithms. Okay, thanks everybody. I think I may have invented a new thing, or at least discovered something really cool independently. Bye.